please.
So, thank you for coming to the Turkish Mathematical Society General Seminars. This is and I would like to thank Professor Stephen Watson for accepting it to give a talk. When we heard that he's visiting Professor Nurettin Çalışkan, so we decided to invite him to give a talk. And so I have to I made a little bit of an inquiry about his research area, and it has a lot of things, so I have to read it from my notes. His work includes, his area of research includes mathematics, topology, analysis, probability, logic, combinatorics, category theory, algebra, machine learning is the same, maybe it's different, and information theory, utility theory, and recently a sub-area of mathematical economics, which is choice functions. And since 2015, I think he's working in the area of choice functions. It used to be a very active area of research in Turkey as well at some point. It used to be Mart Sertel interested in this kind of things at some point. So at the moment his work bridges pure mathematics and applied mathematics in the sense of this kind of applications. So today the title of his talk is Description of all Semiorders and Consequences. And thank you.
Well, thank you very much. It's really a great pleasure to be back in this temple for, I think, the 6th time. It's a wonderful city. We're just having a wonderful time here. Wonderful to see again my old friend, Professor Ergund, and to meet also some new friends here as well. And that's also a great pleasure for me. So just great to be here. So what I wanted to talk about today is some work that I've been doing with a colleague of mine in Italy, in Catania, Alfio Giarrotta, who's at the University of Catania in the Department of Economics, and also with his student, Davide Carpentieri, who's a PhD student working on similar things. And this isn't exactly choice theory, and it's not exactly topology. It's actually, I guess, order theory. But to me, it feels the same. It's all about the same combinatorial flavor, as you'll see. And anything that has a combinatorial flavor is what I really enjoy. Especially if I have to get my hands dirty and I don't have access to powerful tools. I really like that. So anyway, that's the title. This is actually a very old subject. It goes back to about 1860 when people in social sciences began to recognize that the ability to tell the difference between two things need not be principal. In other words, you may be able to not tell the difference between A and B, and you may not be able to tell the difference between B and C, but you might be able to tell the difference between A and C. It's not principal. Poincaré actually gave an example. He said, in the French text, but what he's saying is that you might not be able to tell the difference between 10 grams and 11 grams, or between 11 grams and 12 grams with your hands, but maybe you can tell the difference between 10 grams and 12 grams. It depends on how much of a difference you need to discriminate. That was in 1911, and a few years later, Norbert Wiener, gave an example which is related, involving unit intervals in the real line. And here what Norbert was talking about is intervals of length 1. And the idea is that you would say that one interval is less than a second interval if the whole interval is to the left. If they're crossing, it's not less. Okay? It has to be, the whole thing has to be to the left. for it to be less than. And he pointed out that, for example, the interval from 0 to 1 is to the left of the interval from 1.5 to 2.5, but you can't put anything in between. So there's a gap there. And what actually is more important is that what you notice is something very interesting, and that is that there are no cycles. So at the top, I'm using this double arrow notation to indicate a situation where it's neither to the left this way or to the right this way. So you don't have an order relation. We could say that you can't tell the difference, or they're indiscernible. And if you use that notation, then you don't get a cycle like this. You don't get a strict arrow, an indifference, a strict arrow, and an indifference. Getting back to where you started. Look at what happens if you do. If you start here, and you're strictly less than something, but you intersect K, which is strictly less than L, L cannot intersect I. So you can't get back again. And the same thing happens even if you have strict, indifference, indifferent, strict. In other words, two of each type in a row. I is below J, J hits K hits L, but there's no way L can hit J. So once again, you can't have a cycle. So what this tells you, and what Wiener noticed, is that you can't, in this situation, have a cycle of length 4 with 2 strict arrows in any order and 2 other arrows. And in fact, those 2 properties, which he noticed, are exactly the axioms for a semiorder. That's all a semiorder is. Something which does not have those 2 cycles. And you would think with such a tiny amount of structure, you couldn't prove much. It's very surprising that you could prove a lot. So the term semiorder was actually given in 1956 by Duncan Luce, who's actually a very famous social scientist. He's not a mathematician at all. And he defined it in a little bit of a difficult to understand way. P means strictly less than, and I means indifferent or indiscernible. But this looks a little hard to read, but it's equivalent to say that it's just a reflexive binary relation which doesn't have either type of cycle. That's equivalent definition. Now I put complete in brackets because if you don't have a strict arrow, you could have a double arrow or you could have nothing. From the point of view of semiorders, it's the same thing. So you might as well assume complete and just put a double arrow. Okay. Now, observations, the strict arrow. Yes.
So it's trans, it doesn't necessarily trans.
So it's not. Right, so that's very interesting. So strict arrow is transitive.
Yes.
And the reason is because if you have a strict arrow, another strict arrow, and this type of arrow here, you could always use the identity and then an ordinary arrow, and now you've got the forbidden rectangle. So actually, it is going to be transitive, the strict arrow. But this one here is not a semiorder because you don't have the transitivity. But this one is. Here, this is the same as that, this is the same as that. But here you can tell the difference, and that is a semiorder. So indifference is not transitive. That's what makes it a little bit harder. Okay. So Duncan Luce gave an example which maybe is appropriate to this sample. Maybe it applies to T here. And that is that I may not be able to tell the difference in sweetness as I add a grain of sugar one at a time. But eventually, I can tell the difference. So there's failure, very visible failure of transitivity going on. And this is a good way of maybe trying to write that down algebraically. That for x to be less than y, it's not enough that it be less. You have to have some threshold. And that threshold of discrimination, sometimes what it's called, might be 1 unit. So if x plus 1 is less than y, then you say that x is less than y. So that's the threshold example that was given by Luce. Well, here's how I like to think of it. And this diagram is actually the genesis of the whole paper. Okay? So let me explain. So this is just the real line. Okay? 0, 1, 1, 2, 2, 3, keeps going in both directions. And I'm trying to show the arrows where you have something strictly less. And anything here is strictly less than anything here. Because this is at most 1, and this is no less than 2. So there's at least a gap of 1 between them. From here to here, well, if you go this way, if you go upwards, here you're maybe at 1.2, here you're at 2.4, the gap is more than 1. But if you go this way, it doesn't work. This way it's indifferent. From 1.8 to 2.6, it's only 0.8, it's less than 1. But in this picture, we're not doing really addition anymore. It doesn't matter that we're going +1 or subtracting and measuring the difference. All that matters is that upward arrows, arrows pointing towards the northeast, are strict arrows, and arrows pointing towards the southeast are indifferences, where we can't tell the difference. And the advantage of doing it that way is that right away, it doesn't matter that we're in the real line. Those vertical pieces could be anything. So this, what kind of vertical linear order should we have? So maybe an Ahrenstein line here. These could all be Ahrenstein lines, or they could be all omega 1. It doesn't matter. Any linear order at all is going to give us an example of a semiorder. And the reason that these are going to be a semiorder is because if you try to get a rectangle, let's try to do it. Try to get a rectangle. So from here, we might start by going over here. And then the next step, we have to go 1 more. Now we've gone 3 units over. But you can only go back 1. So you're not going to get back. If you go across 1 unit, and then 1 more unit, to go back, you have to go this way. And now you're not going to get back this way vertically. So no matter how you do it, you are not going to get that rectangle. Again, if you go this way, back this way, up like this, you still can't get back to where you started. So you're not going to get one of those cycles, no matter what linear order you use for the vertical pieces. Does that make sense? Okay. So that helps a lot because it greatly broadens the whole scope of these kinds of semiorders. Now, semiorders have actually been used a lot, and I just wrote down some of the areas. Usually it's in decision analysis or preference modeling, but it's not just in mathematics, it's in economics, it's in psychology, those are the main 2. It's really whenever you have values that are risky or have a margin of error, which makes sense, right, because of the threshold example. You're asking for a margin. And those are 2 reference books on the topic. So there's a lot of work. And I can't say that I read these books, but I've certainly looked at them in depth. There's a lot there. The first book has a set of applications, and you can just see the large number of applications that are given in that book. And those sections are just very short. They're just mostly references to things in the bibliography. There's literally hundreds of papers that use this area. And maybe some of them even sound surprising, archaeology. So it seems a little surprising. And I looked there, but I didn't really look carefully at the papers, or even genetics. Genetics makes more sense, right? The distances between DNA. But anyway, in the finite case, semiorders are quite well understood. You may know David Scott and Patrick Suppes, quite well-known mathematicians. They show that if you have a finite semiorder, then for sure it's one of these. For sure it's a threshold example. So every finite semiorder must look like this. You may have to kind of rescale it to make it look like +1 or reorganize it, but it's still going to look like one of those, and it is going to be with the unit intervals. Okay? It's going to look exactly like the real one. And this has been known now for, what is that? That's more than 60 years, 65 years, this finite case has been understood. as all being threshold examples. But the general result has not been clear. What do semiorders on an infinite set look like? Well, 25 years later, after that result of Patrick Suppes, Manders showed that so long as you don't have an infinite chain of strict arrows followed by one more, going this way, that's omega plus 1, or this way, that's omega plus 1 star. So long as you don't have that happening, then again, it'll be a threshold example. Okay? That's pretty much the state of the art when we started working on this problem. The general case was really not understood. Lots of partial results, but no real description of semiorders. And I think part of the reason for that is that the emphasis was on these functions from the semiorder into the reals. Always trying to represent it by means of a function into the reals, which are called utility functions. And I think that's what maybe prevented things from progressing. But all linear orders are semiorders. So it doesn't matter how complex they are, they're all semiorders because you can't have a chain like that. You can't get back. In linear order, you can't do it. There's no cycle. So, but in the threshold examples, you've got no rule, right? You've just got ordered type of integers. So you're only going to get the integers and its subsets. You can't encompass all the linear orders. You can't even encompass the reals with the linear order. So to describe all semiorders, we somehow need a description that includes both linear orders and these threshold examples, integers times y. We need to encompass both of those in a single kind of description. And it's hard to really see how to do that. Well, I want to give you an example here. This looks a little complex. It's actually not. It's actually easy to think about this as a lexicographic order that has been shifted. Okay? So, I've got 3 coordinates here. And in lexicographic order, what do you do? Dictionary order. It's like sorting words, right? In a dictionary. You look at the first coordinate. If you can tell them apart, you know which one comes first. But if they're the same, you look at the next one. And if they're the same, you look at the third one. That's ordinary dictionary order. But here, we do something a little bit different. We do the old-fashioned thing on the first coordinate, and we do the old-fashioned thing on the third coordinate. But on the second coordinate, we ask not for it to be less than, but to be 2 less than. So not enough to just be 1 less than. We have to have a gap. And so that's the requirement. And what that means is that if you skip 2, this one takes command. And so every arrow from here to here is a strict arrow. But if you only have a distance of 1, then you have to go upwards. Just like in that picture we drew. If it goes downward, it's not going to work. If it goes across, it's not going to work. It has to go up. That's the only way you're going to have it in the third case. So you've got basically 4 different arrows. So this is z times y, then another z times y, another z times y. There's x of those clumps, x of those pieces. And in each piece you've got z this way, and then y this way. If you're in a different clump, you look at x. If you're in the same clump, and you're more than distance 1 apart, no problem, you have an arrow. If you're 1 apart, you look for an upward arrow. Otherwise, there's no strict arrow. So that's how a Z product works.
And why the linear order that you put on each part? Each one is ordered.
Yeah, so each of these vertical ones is ordered by Y. So you only use that when you're trying to decide whether this coordinate is above that coordinate. It's the only time you use it. Okay, it's comparing those. But only in this situation where one is one past the other. Exactly. So you can check can never get back. That's like in linear order. So you have to stay in the same clump. If you're in the same clump and you jump 2, the next time you have to jump 1, you'll never get back. If you only jump 1, you have to go up, just like the argument we gave already. So that argument works exactly the same here. But X lets you incorporate any linear order, and each individual clump lets you incorporate Z as well. So you get both. So that's an example which is good. So you can think of many examples here just to give a very, I'm not going to do anything with this, but for example, you might take the reals as this order type. And you might take 0, 1 as the vertical order. And now you can define this. It's going to give you a semi-order, and they have some interesting properties. But it's just a way that you might define an example. You define X, you define Y, you got your example. You may want to take a subset, because any subset will also inherit being a semi-order. Okay. So, as I mentioned, every subset of the Z part is a semi-order, simply because the definition of a semi-order is that there are no forbidden cycles. If you have a forbidden cycle in a subset, it's already there in the big one. So it's an inherited property. Okay. So the question is, does every semi-order look like this? What other kinds of semi-orders are there? This seems like a fairly general example. But are there more examples? Or might it be that all semi-orders are a kind of shifted dictionary order? That's the question. Okay, so let's try. Let's start with a semi-order. We know nothing about it, we just know it's a semi-order. And let's try to see if we can write it as a shifted dictionary order. So this is it's going to be a big job because we're starting with W. We have no further information. We have to come up with X. We have to come up with Y. And then for each W, we have to decide where to put it. We've got to figure out which clump it sits in, number 1. We have to figure out which bar in the clump it sits in. And then we've got to figure out where the bar to put it. So we've got some work to do, and yet we know nothing about the semi-order, so we don't have a lot to work with. And this is where it's quite surprising how much structure is present just from the non-existence of those cycles. So I'm just going to approach those questions. The first question, the first thing that we can do is we can look at this semi-order and we can take its transitive closure. As we mentioned, a semi-order is not transitive. Only the strict order is transitive. The semi-order is not. But if we take the transitive closure, it becomes transitive. So it becomes a linear order, except that there's equivalence classes. Okay? If we mull it out by the equivalence classes, then we get an actual linear order. And that linear order, that's going to be our X. That's it. That's the X order. It's just the transitive closure modded out by the equivalence classes. And if you want to know where a point goes, you just send it to the clump indexed by the transitive closure of that point. And without spending too much time on it, I'll just say that that works perfectly and easily, and there's not much to say, unlike a lot of the rest. So this part is actually quite easily done. So from now on, we'll just assume there's only one equivalence class. And that means that now we're just going to try to figure out how to finish off the question. In other words, we've got 3 questions left. We decided which clump to put it in, but we still got to decide which bar to put W in. We have to decide where in the bar to put it, and we have to decide where's Y. And each of those will take some work. Okay, so is that any questions? So now I have to get a little bit more technical, but just look at this topic, n of x, y, okay? You've got a point x and you've got a point y. X might strictly arrow y. And it might be that you can find something in the middle, so you can find a long chain of strict arrows from x to y. And if you take the supremum of the lengths of those chains, well, if x doesn't arrow y strictly, then the supremum will be 0. But if it arrows it and there's nothing in between, it'll be 1. But a priori, it could be infinite. It could be that you have chains of arbitrarily large length. Strict chains between x and y. Turns out that can't happen. Just from the axioms of the semiorder. So to do that, let's see why. So look at this. Suppose you have this situation that r arrows t. It might be strict, it might not. I'm not saying anything here about what it is, but you can think of it as a double arrow. R arrows t and t arrows p. I claim in that case, the longest chain you could possibly have from p to r is 1. And the reason is,
chain, but isn't this a chain?
this is just a
Okay.
it might be strict, it might not. Yeah. So if it was more than 1, then let's say it's at least 2, you can always collapse 2 to 1. So you would have this situation. And if you've got this, look at the problem. Strict, back. Forbidden cycle. So you can't have the outer contradicting assembly. So that's the first thing. Second thing, if you have an arrow from Q to R, like up here, then these numbers are related. It's a little hard to read this, but let's just follow it through here. So, first of all, we're assuming Q arrows R, so I'll just write it down here. Now, we know that R and P are in the same transitive closure. That means there is a path from R to P. We don't know if those arrows are strict or not, but we don't care. There's a path from R to P. So you have this situation for sure happening. Now, suppose for a moment that you've got a path from P to Q. And it has length of these 2, so at least x exists. Maybe x is the same as P, or maybe it's not. But you've at least got a path from P to x to y to Q of length of these 2. Now, look at this situation here. Strict, back. This can't go back. Or we'd have a cycle. So from x to r, it has to be strict. And if x to r is strict, that means that we've now got a chain going all the way to x and then to r. And what is the length of this chain? Well, just 1 less than that. So p, n of pr is at least n of pq minus 1. Now, from there, we can show that all these numbers are finite. I know it's hard to remember the slide, I'm just repeating. The proof here is that's just the previous thing we just proved. Okay, we just proved this. So I just repeated it here. And that's enough to prove this. Because if Q arrows are, if this doesn't happen, then my conclusion is already true. So you might as well assume it happens. And if it happens, then this happens. And if this happens, and this is finite, then this guy is also finite. And that's enough to get this, because to prove that, again, we know that there's a path of some kind from Q to P. So we'll call it Q to R to something, assume it's of the shortest possible length. And because it's the shortest possible length for having infinite length, for having infinite n, this one has finite n. But then we just apply part 1. And we get that for P to Q also is finite. So actually, from any point to any other point, there is a maximum on how long these strict chains can be. Surprising, I think, actually. But it's really necessary to have that. Okay. So now, this is actually a classical notion called the trace. And you might even know of the trace. It's been used in a number of different contexts. But let me just look at it this way. So look at P here. There are some things that arrow it, and there are some things that P arrows. The blue triangle here are all the things that arrow P, strictly. And the blue triangle here are all the things that Q arrows. And then the yellow triangle is all the things that arrow Q, and the yellow triangle over here are all the things that Q arrows. And when you draw that picture, what is kind of surprising is that what will always happen, regardless of the relationship between P and Q, it will always happen that either this happens or the reverse. So here you can see, we'll call this, the blue one, we'll call it the A. The AP, sorry, not the blue one, the one on this side we'll call the A. The AP here you see is less than the AQ. But the AP, the BP on this side, the big one, contains the BQ. Okay? And that's always going to happen one way or the other. So this trace that we've defined here is actually a total order. It's a total order. Given any P and any Q, they find themselves in a total order. In fact, it's a linear order, except that they're read the equivalence classes you can't tell apart. So that's what the trace is. And that's actually a classical notion. We didn't invent that. That's been around for 20, 30 years. You could think of it as this way. You could say that P is less than Q in trace. It just acts small. You may not have arrows between them. It may just be a double arrow. But it acts small. But the surprising thing, and I couldn't find an attribution for this, but it's at least 25%. That's a linear order. Okay. So I was asking about what bar are we going to assign our W to. All we're going to do is we're going to fix some B. It doesn't matter what it is, just fix a B. And look at whether you have a chain to B or a chain from B, or maybe neither. And if you've got a chain going towards B, then you're going to map it to the negative of the end. Okay, this is hard to read, but let's just go to the next slide so you can read that. Okay, this is all I'm really saying. Okay, that if there's a chain of length 1 to B, if that's the maximum, put it in the negative 1 bar. If there's a chain of length 2, put it in the negative 2 bar, and so on. And if there's a chain not to B, but from B, of length 1, put it here. We need 2 here, so I have to skip up to 2. I can't put it at 1, I need an extra space here. So if there's a chain of length 1, put it at 2. If there's a chain of length 2, put it at 3, and so on. And we know that all of these ends are finite, so one or the other has to happen. Or maybe there's no chain at all between the two, in which case we'll just look at the trace, whether it's above B or below B. And where do we put B? Well, I'll put it at 0. Could have put it at 1, but we'll put it at 0 because we have to put it somewhere. And that's it. That's really all that rather hard to read definition says. It just says do that. And it turns out that works. That's exactly what you need to do. All based on these longest chains. It doesn't seem like it's too readable when you look at it that way, right? But when you look at it, and that bar, we're just going to call it F. Okay, so that's the place we put it. And you'll notice, I mean, as mathematicians, you probably had this reaction looking at this picture. You said, no, that should start at 1. This is ugly. This should place. We shouldn't have two places here. There should be one place. This should be 0, and these ones should start at 1. This is ugly. And I agree with you. It's very ugly. I don't like it either. But you don't have a choice. You have to do it. Because this thing, remember, is a semiorder. Can't tell the difference. Can't tell the difference. But here there's a strict order. So these have to go in different slices. But these two, what are you going to do with them? You can't put it, if you put them in the same slice and these in the same slice, you're doomed. So you have to somehow put these two in different slices from this one. So what we chose to do is to put, let's say, these two together at 0 and this one at 1. There's no way around it. So, but it's reality. So we have to do it. So, okay. So what do we have to do now? Now we have to worry about the other situation. In other words, we need these arrows to be strict arrows and these ones to be indifferences. And we haven't even defined what y is, much less figured out why this should tell us when there's a strict arrow. What we've done already, however, is enough to get these two. Just that assignment gives us this. If you skip by 2 bars, for sure you're going to have a strict order. Guaranteed. Regardless of what the y is and regardless of where you put it in the piece, regardless of any of that, it's going to happen. And regardless of what you do, this is also going to happen. And whenever you have a strict ordering, they're going to have to, one's going to have to be the right of the other for sure. But so far we don't know this part.
So what was that again?
Pardon?
What was the F?
The F is just the number, the slice, the number, the label of the bar. Yes, right. The label of the bar. So yeah, so we need this whole if and only if. We've got some of that here, but we're not quite there yet. But maybe just to give you a little bit more flavor, let's just look at an example. Supposing we put x in slice number 2 and y in slice number 4, bar number 2 and bar number 4. We should have that there's a strict arrow for x to y. Okay, so suppose not. Suppose y arrow x. So remember, 1 less is the n of bx. So n of bx is 1, n of by is 3. So it means we've got a chain from b to x at length 1, maximum, and a chain from b to y at length 3, bsty. And since we've got this arrow back here, we can't have that. Let's see why. Because strict, back to x, can't go back. It must be strict from s to x. And s goes strict to x, that means we now have b to s to x. And that contradicts maximality in this guy. So just in this special case, you start to see a little bit of the flavor of how that's enough to show you that when you're distance 2 or more apart, you automatically get the strict arrow. And there's lots of other cases, but they're all kind of similar. It gets a little bit harder when you're dealing with the 2 center ones, the 0 and 1. Anyway, just to give you an example. But still, what we need is that when you have 2 points, one of them here, x is here, and y is here, we need that the strict arrow happens only when you're going upwards. That's what we need to show. How do we do it? And what is y? So to do that, I have to talk about something that actually gets kind of interesting geometrically. I'm going to call it back. Okay, so you remember that when you go this direction, you can go back. So long as it points southeast. So long as it points northwest, you can do it. So you can keep going northwest. And maybe you can get, depends, we don't have the whole bar, right? We just have a subset. So as you're going from P to Q, maybe you can find one of these paths back to Q. And if you can, then we call that a back path. Okay? Really, the picture tells you all you need to know. This just says that going back.
Consisting of indifferences.
Yeah, consisting of in fact, if I just said an arrow, it would be equivalent, right? Because you're not going to have a strict arrow going this way, so yeah. So that's the back. So we're going to define a total preorder on W by the following method. So best thing is to try to explain the picture, okay? So let's find the things that are above P in this order, above P. If you can find a backpath to Q, it's above it. So anything is, so this is, let's say, the lowest possible backpath, and then anything above that will be above it in that order. But also anything here that can't go back to P, that is too high to go back. This guy's trying to go back to P, the best thing to do is get to here. So it's also above P. This one again, it tries to go back, no matter what it does, it's above. So those guys are also above P. Okay? That tells you what the ordering is. That picture. That's how you tell that.
Everything on the green part can go back to P.
Yes, everybody on this side up to here P can go back to everything here, but nothing here can go back to P. so here says P less than Q in the trace. I didn't mention it, but in the trace, these are the guys that are less. These are less than P in the trace. Okay? And so they're less than P in the trace, but there's no backpath. Here, P is going back to Q, so here there is a backpath. So either way is a way for it to be less than equal to it in D. And the definition, again, I find this a little unaesthetic, honestly. And it's kind of surprising that when you work with this, that this is, in fact, a partial order. It's actually a partial order, but it is, it's expensive. Not only that, it's even more surprising, perhaps, that it's a total order. But it actually is a total preorder. Basically, it's a linear order, except for equivalence classes. When I say total preorder, I just mean linear order, but there might be equivalence classes. So that's this total preorder, and that's going to be what we use for Y, this order. So Y is just the whole semiorder with that total preorder as the order. So you can either think of it that way, which is a little hard to conceptualize, or you could think of it, the bars as being really just W with the trace, except we're going to move the bars to make this line horizontal. In other words, shift this up to make that horizontal, shift this up, and for every other scheme like that, shift it up to make all those lines horizontal, and then you can just use the trace once you shift it like that. So either way, it gives you this Y, and it tells you where also to put W. You just put it at W, because we're already saying that the bar is W. Okay. So here's the general result, and that is that if you have a semi-order, this actually works. The strict order happens if and only if either it's less than the transitive closure, or it's equal, and you've got a gap of at least 2, or the gap is exactly 1, and it's less than the new order. That's it. That's a complete description of every semi-order, so it looks like the bottom picture. Or you could also think of it this way, that being a subset of Z product of any linear orders, and being a subset of the Z product of these 2 linear orders, they're all just alternate ways of describing all semi-orders. Right? We just finished proving 1, 2, 3, or leaving outline of the proof. There's actually a lot of details, especially on the D ordering. And we checked this one already, and from here to here is just a special case.
This classic product notation is, I mean, does that embed in W1?
Which notation?
This classic product.
The assessor product. Yeah, I don't know, maybe it's a bad notation, I don't know. The idea is that it's in times, but it's got this strange middle factor, which is Z. But it's not an ordinary product because of this +1. And I couldn't find a good symbol for it, but it's not supposed to really indicate tensor product. Yeah. But, you know, I looked through the latex symbols. Actually, I looked through the latex symbols. He said this is the best way you have it. So I said, okay. Seems okay to me. It'll confuse people who work with tensor products. Okay. So basically, the result is every semiorder looks like this. Every semiorder is a kind of shifted dictionary wording. And again, I find this very surprising, starting from these axioms, that you can get this kind of structure. So, if you look at some of the classical results about semiorders, like for example, the Scott Suppes one that I mentioned earlier, about this mapping into the reals, it turns out you can just identify them. Instead of being x times z times y, it's just a single point. You don't need that first factor at all. And down here is the reals. That's it. That's a description of the Scott Suppes representations. And often when you're looking at properties of semiorders, you get this kind of a situation. And I'll give you a couple of examples in a minute. You've got x and you've got y, you say what they are. And then you say something like, well, for every point x in the first coordinate, there's only n points which extend it. And maybe for every x and I, there's only m points which extend that. Things like that. You just think of it as a tree, right? Going x, z, y. And you're restricting the branching, basically. And here I said for all but countably many. So there's maybe restrictions like that. But a surprising number of classical properties of semiorders have descriptions just like this. So just to give you an example, topologically separable. It means count within second. It turns out that the first factor has to be reals. The last factor has to be reals times q. Reals times rationals, ordered lexicographical. And the restrictions are that for all but countably many reals, you only have almost 2 points extending it. And for every real I and R in the first coordinate, there's at most 2 rationals you use. So that's an example. In economics, they care not so much about topologically separable, but they care about more is what they call the root separable, which is very similar except that you allow it to be equal to the endpoints. Kind of strange from the topological intuition, but I understand why they use them. And for that, it's again a very similar inscription, right? It's got this same kind of form, that for certain restrictions, you restrict the cardinality. And we have a whole list of properties which just look like this. They're all restrictions on branching degrees. So I'll just conclude with one more thing. There's a classical result by Wiener from 1978 about the dimension of semiorders. This is a beautiful paper in the Journal of Computational Theory. And Wiener showed that the dimension of any semiorder is 3 at most. And that means that it's the intersection of 3 linear orders. And I want to give you a proof of this fact using this description. And I think it's maybe a little bit short of the proof of the image. So that's why I want to show it. And I think it gives some intuition. So I'm going to give you the 3 orders. Here's the first one. So as you know, we've got several of these blocks, and I'm just going to tell you what we do in each block. In this block, we put together the pairs, 1, 2, 3, 4, 5, 6, and we use the B ordering on 1, 2, the B ordering on 3, 4. Well, we put this whole block to the left of this one. So normally there's arrows going this way, but no, we just cut it here, put this to the right. That's a linear order because this is the linear order. And the second linear order is this one, just shifted over by 1. Same thing exactly. second here. First of all, anything that's actually less than it is less than it here. This linear order is an extension, because if I have an ordering, it either is across one of these boundaries, so the linear order is bigger, or it's within this block, in which case it's going to respect the less than b. And the same thing here. And here's the last one. We just put each one separately. We put every column to the left of every other column, but inside we use greater than. We turn it upside down. Again, the linear order, because we're just putting linear orders ordered linearly. Why does this work? Because if we had something which has distance 2, here it's bigger, here it's bigger, here it's bigger. If it's distance 1, well, let's see. Here it's less than b, here it's across a boundary. Here it's across a boundary. But we don't get anything we shouldn't. Because if we have something this way, we don't want the ordering. Here we have it. Here we have it, but here we don't. So it's going the wrong way. And going vertically, here they're comparable, here they're comparable, but here they're not, because it's greater than, the other one is less than. So those 3 pictures, that's it, that's the proof of the theory. So having that ability to represent the semiorder this way just gives you this very strong geometrical intuition that you can bring to bear on these questions. And it helps you not get lost in the ocean about it. So, anyway, so those are the 2 papers, and I just wanted to thank everyone for listening.
Any questions or comments? I was wondering, is this the Rabinovich? There's a Rabinovich trick.
Rabinovich.
Is this the same Rabinovich? Yeah, I'm saying, so...
He's a mathematician, he's combinatorist, yeah. So is it the same guy?
The trick is, instead of writing x times y is not equal to 0, you write, I don't know, for y is not equal to 0, or variety is not equal to 0, it's like y times, there's an x such that y times x is equal to 1. It has an inverse in a field theory.
Oh, okay. Interesting.
So,
That sounds combinatorial.
so not equal to 0 is an open condition.
Mm-hmm.
You can turn it into a closed condition by, this is called Rabinovich trick, but
I think it sounds similar because it's kind of a logical trick, right?
Yes.
And I think that seems to feel similar to me, to be working on this kind of thing.
John was interested. Matematik psychology.
Yeah, totally. Well, they actually publish a lot of mathematics in the journal. It's really kind of interesting how much they publish. I mean, some is in a language that is on first sight doesn't appear to be so mathematical, but then when you open the article, first of all, they don't do things like we do. What they do is they have this paper with a lot of discussion and a lot of theories. Where's the mathematics? Because they put it all in the appendix. So each result is stated, but the proof is not in the paper. The proof is in the appendix. It's just the tradition of mathematical psychology. Makes sense. So the only way for a mathematician to read a psychology paper is start from the back, but you decide it's the kind of mathematics you like. So that's how you read it.
So that's what machine learning is also.
Pardon me?
It's the same with machine learning. They put the results and then
Okay, done. So thank you again.